Good afternoon, everyone. Welcome to the USACM webinar series of this technical thrust area, nanotechnology and lower scale phenomena. My name is Nikhil Admal. I'm an assistant professor from University of Illinois, Urbana-Champaign. Today, it's my privilege, an honor to introduce the webinar speaker, Professor Gábor Csányi. He's a professor of molecular modeling at the University of Cambridge. Professor Csányi is an expert in atomistic simulations, particularly in multi-scale modeling that couples quantum mechanics to larger length scales. His work, he's also interested in statistical problems involving sampling methods to explore configuration space of atoms or molecules. He helps run the Leonard Jones Center in Cambridge, which brings together modelers who work at the atomic scale. Professor Csányi received his bachelor's degree in applied mathematics from Cambridge in 1994 and his doctoral degree in computational physics from MIT in 2001. Subsequently, he worked at the Cavendish Laboratory before joining the Faculty of Engineering Laboratory at Cambridge in 2007. His current research focuses on applying machine learning and other data-intensive methods to physics, chemistry, and material science. And in particular, he focuses on constructing interatomic potentials from ab initio electronic structure data. So before we begin, I request all participants to mute their microphones. And if you have, the current talk is being recorded. Please post your questions in the chat window, and I will facilitate the discussion towards the end of the talk. Professor Csányi, the screen is yours.
Thank you very much. It's a pleasure to give this webinar. I'll try and speak for about, let's hope, 45 minutes, leave time for some questions. So the title is Foundation Models for Materials Chemistry. So, okay, this is the sort of obligatory multiple scales of materials modeling slide. I won't spend too long on it, but you know, the sort of provocative, maybe aggressive capability scales and even more provocative errors here. But really, the point of it is just that that when we try to do first principles modeling, which is actually a minority of how, in the grand scheme of things, how science is done, we really try to go from below, right? So there is we can solve the Schrödinger equation exactly for very few systems, a bit approximately for larger systems. And the idea of first principles modeling is to go up this chain, always making controllable approximations, controllable or verifiable approximations, rather than making models kind of top down, which fit to something higher up. And because when you do first principles modeling, if you control those approximations, you get things right for the right reason. And we're bringing in ML technologies, machine learning technologies, essentially function fitting, high dimensional function fitting. And the goal here is to go from this region where we have very significant accuracy, principally due to density functional theory, sometimes go down to wave function methods, and bring them up in capability to sort of hundreds of thousands of atoms or microseconds to the world of force fields, where we want just trajectories. So the electrons are auxiliary, and that idea is what I guess distinguishes force fields from an electronic structure treatment. And in that, we hope to gain, we do gain, sort of, you know, factors of 1 million, even for very small systems, for which we can run these density functional theory, for example. And the idea is controllability, so that you don't lose accuracy on the trajectories, on the forces and energies. And of course, because everything is about convergence and controllability, is that you don't lose accuracy in the observables that you compute. So really, the fact that we should want to do this and that this will help materials modeling is really based on the success of ab initio molecular dynamics. So when you stick to the 100 atoms and picosecond timescale on which at which you can do the electronic structure theory. Ab initio, molecular dynamics has really become a microscope for atomic scale processes, and has had, you know, overall several Nobel Prizes awarded for it, essentially, and allowed us to model systems in conditions and with some precision that really wasn't possible before. So just random examples are, you know, phase diagrams for all kinds of materials under all kinds of conditions. So liquids, aqueous solutions. Here's an image from a paper on polyatomic ions, where you get ionization potentials that you can measure experimentally. And of course, surface science is another huge area which has benefited from ab initio methods, ab initio modeling, where experiments and electronic structure, molecular dynamics have kind of basically almost touch. So the experiments can almost go down to atomic resolution and can probe processes which with some further controllable approximations you can model using density functional theory. And really the whole first principles modeling is there to predict material properties, catalytic reactions, properties of drug molecules, semiconductors. These are just major areas where we're doing the right thing. Quantum mechanics is the way forward. But of course, it's very expensive. So this is a graph of a chart of what codes are being used at the UK's National Computer Facility. It's a couple of years old, but hasn't changed very much until last year. And you can see that 35% of the UK's academic supercomputing is spent on running VASP, essentially DFT, MD. And if you add up all the other green bars that are just other codes doing the same thing, then you get about 40%. So 40% of the UK's national computing is spent on doing energies and forces with DFT to move the atoms a tiny bit and then carry on. So that's about to change, and it's about to change due to our ability to fit ML potentials very accurately enough. And I have a brief graphical history of the last 15 years of ML potential. So up to 2007, we could fit make low-dimensional fits. So molecules with a few atoms, maybe a molecule, diatomic molecule on a rigid surface. And these were sort of sporadic pioneering work. And the idea is that there is a complex potential energy surface in reality is involving many atoms, but you can't really access it. You focus in on some small minimum or some small dimensional subspace. Then post 2007, the introduction of, based on the work of Jörg Behler and Michele Parinello, were high dimensional fits. So that means that you can now do the same thing, fit accurate potential energy surfaces for many atoms, where you can get data. So this is illustrated by these curves here, that you have some complicated potential energy surface, which if you sample it with by generating first principles data there, then you can fit it accurately. And there's 15 years of technology post 2007 in how to do that well and efficiently. And really the change that's happened sort of end of last year, and that will sort of we'll come to that in the second half of my talk, is potentials, ML potentials, which have very wide transferability, so very vast generalization. And the way to picture this is that you give it little data, little in the context, in the sense that only near minima of let's say inorganic crystals, and that potential can then generalize and do all the chemistry that you want to do. Not super accurately necessarily, not as accurately as if you had data there, but certainly well enough for sampling, well enough for exploration, and then you can fine tune later for accuracy. So that's the story that I want to tell you. The way we do ML modeling is that, and this is what started in 2007, is that you have some descriptor of the atomic environment here, and maybe you have a way to compare them. And then you have a regression scheme. Here in this box, I wrote Gaussian process regression. That's how we started it, same as kernel regression. But neural networks are, of course, even more widely used, and we use them ourselves these days. And then you need an application. So now you need to predict something, and that could be atomic energies, forces, the derivatives of those, or it could be other properties. And there's lots and lots of work going on in predicting, for example, the chemical shifts, the delta ISO value, NMR chemical shifts, or polarizability tensors, and so on. And so it's a little bit more detail. You take data on size of systems that you can afford with the electronic structure method, and that gives you points on the potential energy surface. And then you have this interpolator, which uses the representation and the regression, and then you test. And that if the potential energy surface is not good enough, if it's leaves you wanting for some accuracy, then you go back and according to some scheme, and you generate new data that's appropriate to what you need. You refit, and you go around this loop. And one of the early worries when a few of us have started down this road more than 15, 16 years ago is how many times you would need to go around this loop. Is it that the case that every few steps, every 100 femtoseconds, if you simulate a large system with MD, you would encounter very large errors, and you would need to do quantum mechanics and refit? And at that point, the method is may be able to engineer it in some niche application, but really not very useful. But that really hasn't panned out that way. This idea really works, and you don't need to go around many times. 1, 2, 6 early on, that's coming down, but really just a handful of times, and you get decent potentials that then you can go and work with. This is a family tree of not even potentials, because that wouldn't fit on the screen, but geometric descriptors. So the ideas that people have used to describe the local atomic environments. And of course, it starts with Lifson type force fields, bond distances, angles, and so on. And in this top, I indicate global representations of molecules and materials also, where you don't break things up into local objects necessarily. But then here, my own work started in 2010 with the smooth overlap of atomic positions, and that has given rise to a whole bunch of other representations using what is essentially the density trick. I'll talk about this in a little bit more detail, but it basically is a many-body representation, just like bonds and angles and dihedrals, but it scales linearly with the number of neighbors. So you don't pay an extra cost for going to high body order. There's a whole bunch of methods here, which are GNNs, graph neural networks. And that's, in fact, also what MACE is. And that's, again, the second half of the talk, the method that we use now. But I want to chart the evolution of this technology using SOAP, ACE, and MACE, because they are building. It's just my own work, and they are building on one another. But I want to take you back to 2014, which is really the first time that we started, after playing around with toy systems and inventing tools and then spending years learning about them. We first saw the first glimpse of what accuracies are possible for large systems. So this is from a paper in 2014 on tungsten, where the training data consisted of very small, just 100 atom structures, and then at the end we were computing observables on tens of thousands of atoms on these locations. But when you wanted to look at the available potentials for something like tungsten, you had the Finney-Sinclair model in EAM, a modified EAM in the 90s, and then the bond order potential in the noughties. And what you see here is that their accuracy isn't really improving. They capture slightly different aspects of the physics and a bit more sophistication in the functional form to capture something essential to the behavior of the material, but not really fitting in with the first principles ideology and method of approximating the ab initio energies and forces controllably. And when we turned on this Gaussian approximation potentials, then this is the sort of accuracy that was possible for the crystal defects. And you see the details here. So just all database cells are small, couple of 200,000 atomic environments, but a few thousand DFT calculations. And it's a high dimensional fit with 10,000 basis functions, giving you an accuracy of about 1 millieV per atom. And that hasn't, so by the way, that hasn't changed. So the accuracy that one can get these days with the much more modern methods and more data is also about 1 millieV per atom. But nowadays, for a much more diverse set of structures than just PCC tungsten. And about 1 millieV per atom is what we need to predict properties accurately. That is also a new result, not of mine, but of the whole field, that if you have a fit that's accurate to 1 millieV per atom, then lots and lots and lots of microscopic properties come out correctly. And that's incidentally, in materials, the millieV per atom limit is sort of what you can get due to K-points. So finite K-point sampling of the DFT gives you about 1 millieV per atom error. Of course, you can put more K-points. The cost is linear, but becomes just very, very large. So typical, very well-converged DFT calculations would have this kind of error. So to give later on, 10 years later, 2020, I guess, this picture from. So 6 years later, we could do this for carbon, for all forms of carbon, much, much more varied than just BCC tungsten. And you get this sort of accuracy, similar plot, right? So these are formation energies of various defects, and the empirical potentials are the gray, and the target and the model are the black and the red crosses. So similar 9,000 basis functions, 6,000 DFT calculations. And here's the millionfold speed up on smallish systems. So lots and lots of applications are now being done. So I would say, again, perhaps a controversial statement, but I would say that materials modeling, atomic scale materials modeling, has been revolutionized by these technologies, and are now routinely being used for all sorts of new scientific applications, used by people who haven't developed these methods. Here are some examples. So here's an example from Carsten Reuter's group from Berlin, the Fritz Haber Institute, and they used, this happened to be my framework, my model. This is a soap gap model where they looked at iridium oxide surfaces, and you create a potential using iterative training, and then you're able to sample millions of structures using simulated annealing, and you discover completely new kinds of structures that haven't been seen before, but then match and resolve puzzling experimental images of iridium oxide in the under reductive conditions. Another example is from Michele Ceriotti and collaborators, where it's phase diagrams. So I mentioned that ab initio is very good for phase diagrams for simple things, but really when you want to go to finite temperature, it gets very difficult. And for something like hydrogen, the number of structures you need to evaluate and to pass through all those phase transitions, you really need an ML potential. And with ML potential, it's easy rather than heroic. And so here in this paper, they looked at high pressure liquid hydrogen. Another kind of work is from the group of Volker Deringer. He's a professor in Oxford. He used to be in my group. And they use phase change. They investigate phase change memory materials. So this is germanium antimony telluride. And they can really reach device scales. So the scale of this is like one of these cross-hatched devices, and you have about 500,000 atoms of this phase change material between this pair of electrodes, and the electrodes, you pass current, Joule heating changes depending on the pulse shape, will amorphize or crystallize this material, which then shows different electrical behavior, electrical properties, and that's how you store the bit. But this is a relatively fast change, so you need maybe 100 picoseconds to simulate this properly, but we can reach that. So we can, with the ML potentials, which are based on accurate DFT calculations, you can access the length scales, 500,000 atoms, and the time scales, tens of picoseconds up to 100 picoseconds, and really model the system as it is created in the laboratory, as it is used in reality. So we reach together atomistic simulation and experiment. Here's another example, again, a collaboration with Volker, is amorphous science, so amorphous silicon science. This is 100,000 atoms, and after making and validating a model, you can do a 200 picosecond compression and study the pressure-induced crystallization. So here's sort of a snapshot, 5 snapshots of this material as it goes from 11 GPa to 20 GPa. And you see that at 20 GPa, you have recrystallized in this single sort of a simple hexagonal crystals. But the coloring here is coordination. And what we've observed here and what the simulation revealed is that during this collapse of the volume, about half the atoms are over-coordinated. So you get to this sudden collapse where the silicon atoms are 10 to 12 coordination. And then they open up. Then the structure opens up to this simple hexagonal structure. And okay, so let me show you with equations how the technology evolved. So in this early work, the smooth overlap of atomic positions representation, you take each atom and atom I, and atoms J are its neighbors, and you build this neighbor density. So it's a little Gaussian, as is shown here, centered on each neighbor, and we form this neighbor density rho I that's centered on each atom. And then we expand that neighbor density using an orthonormal basis. So these are some orthogonal radial polynomials, Rn of R and YLMs. And the expansion coefficients C have this property if you take the limit, we had lots of work where we had the limit sigma is finite, but you can take, for what I'm going to show next, it's easier to think about the limit of sigma going to 0, where the expression for these expansion coefficients is very simple. You just substitute the density rho and integrate, and you just evaluate the radial basis at the positions of your neighbors. And this sum over the neighborhood is essentially the density trick. So you can get these expansion coefficients with a single sum over the neighbors. And then this achieves permutation invariance of the representation. And then to get rotational invariance, you simply take a product of C dagger C and sum it over the M index of the spherical harmonic. And this gives you what we back then called the SOAP representation. It's also called the power spectrum. It has 3 indices, N, N prime, and L, and we make the model a function of this P. Now, Ralph Draughts came along in 2019 and generalized this work in looking back, a rather straightforward way, but nobody really, apart from him at that time, saw through all of this. So his generalization says that, look, this R function can depend on many things. It can depend on L. It can depend on the elements. And let's call this combined basis function of R with many, many indices and YLM the pair basis phi. And then you sum that pair basis phi on your atomic position. So he jumps through to this sigma goes to 0 limit and calls it an atomic basis. It's exactly equivalent to the C here. I'm using the notation of each paper. So in the SOAP papers, you will see it as C. In the ACE papers, you will see it as A. And then so far, it's basically the same, but now comes the generalization. So this is the key insight of Ralph, that you don't need to stop at forming C dagger C. You can actually make an arbitrary size product. So you can take arbitrary number of this A, which is the same as the C, and multiply them together, and you get a tensor. And this tensor, you can do the same kind of symmetrization operation that we do here to a general A tensor, no matter how many times you've multiplied it with itself in this tensorized way. And that is that's using the generalized Clebsch-Gordon coefficient. So the CLM are coefficients in the textbook can generate them using a recursive formula, and you get this B basis that And this B basis is a linear orthonormal, linearly complete basis set for symmetric functions for the neighborhood of an atom that obeys permutation invariance and rotational invariance. And it's complete. So any function that is permutationally and rotationally invariant can be written as a linear function of these B functions. And then the most modern version of this, which is MACE, the M stands for multi or something like that, but we just call it MACE, is essentially that you do this not once but twice. So it's the idea of a message passing network, but the equations that I'm showing you are exactly in the MACE paper, but I've arranged them so that they show the correspondence. So we have a pair function, we have a radial basis and a YLM. I'll come back to why there is a Clebsch-Gordon, a generalized Clebsch-Gordon here, and what H is, but actually in the first iteration, they aren't there. And then we form, we sum over the neighbors, J here, we take the product of arbitrary number of A's, and then we form the Clebsch-Gordon, using the Clebsch-Gordon coefficients, the B basis. But then we don't stop, but we take this H function is initially just a very simple embedding of all the elements. You can think of them as delta Z I Z J of the element. But then we linearly combine them with the B basis, and we do this, we go through this whole expansion one more time. So we take these H functions, which is initially just a linear combination of a delta function plus the B basis with some coefficients that we later optimize. We come back and we go through, we form another phi, sum them up for another A, do another product, and finally symmetrize. And that's our model. And we then fit the energy to the second round. So it's sort of the same idea of ACE, but done twice. And there are lots and lots of things to optimize here. So all the W functions, W here are matrices, which initially are just random, but then you optimize them to fit the model. And that's the MACE model. So it is not a linear fit like ACE, but because the degrees of freedom in these W's are all multiplied together, but it builds on this atomic cluster expansion idea, and the nonlinearities here are kind of simple in some way. So why are we doing all this? What's the benefit of all this? Here's an example which shows this in some dramatic way. So here's an example from recent work, which is sulfur liquid. So you have this, imagine a sulfur crystal that you melt, and at high temperature and pressure, we take some data and we fit soap gap. And we get total forces that are sort of okay, but if I decompose them to intra and intermolecular forces, it really is essentially garbage. There is no good decomposition. When I turn on ACE and higher than quadratic multiplication of that atomic basis, the C and the A, so you go to high body order, then you get a much better idea of what the intramolecular forces are. The intramolecular forces, which are much, much smaller, are still very poorly described. And then you turn on MACE, and suddenly, from the exact same data set, it's able to disentangle what are intra and what are intermolecular forces, essentially due to this second message passing layer. So the next question, which I didn't really ask, other people have, but I was sort of trying to ignore it for a few years, is can we use all these technologies to build general machine learned force fields for materials? And Xu Pingong was the first person I know who kept pushing and pushing and asking this question. So he made models as early as 2018, and then later evolutions, where he focused on materials discovery, fitting potentials, evolving frameworks of potentials to the materials project data. And he did structured relaxations. And that was okay. I thought that those models will never be as accurate, never be as useful as application fitted models. So I didn't pay too much attention until students at Berkeley asked our help in fitting our model, our MACE model, to the materials project. And imagine that this is the MathBench discovery benchmark. So imagine the data is like this. You have all known inorganic crystals. Most of them are less than 50 atoms. 90% is less than 70 atoms. And so it's about 50,000 experimentally known inorganic structures and another 100,000 ab initio derived structures in their database, and 10 configurations from each relaxations of these structures using DFT-PBE. And with a little bit of help, this is data from about a year ago, sort of almost to the day. Mace was the top of their leaderboard. What does their leaderboard mean? Well, it's about predicting, it's materials discovery. It's about predicting energies of unseen new crystals, again, small inorganic crystals that are not part of the training set. And here are lots of these earlier attempts by people near, in and around Berkeley and Xu Pingong's group. And this then became a big fashion, and it didn't take very long for others like Google, GNOME model here a few months later with a much, much bigger data set. So instead of 1.6 million structures based off of 150,000 distinct geometries, they used 6 million distinct geometries and 90 million training structures. And you can kill this benchmark. You can get much, much better prediction of energies of new crystal structures. Okay, fine. One can play this game. And then, of course, since then, this game has been played, as you can see. There's MatterSim from Microsoft, Orb, and Meta's model Equiformer V2. These are really rather unsmooth models, really not really that suitable for molecular dynamics, but they do extremely well on predicting energies of unseen molecules. When you turn on something like how well do they predict phonons, and this kappa SRME is a relative energy of thermal conductivity, where you need to do phonons and anharmonic phonons, then the picture suddenly looks very different. And here, the smaller the better, and the smooth models that Mace produces using this ACE atomic cluster-based expansion again show their worth. So really, that's fine. That's about materials, but really, are these models any good for anything else other than predicting small molecules, small crystal structures? And really, it was an accident. We needed to show something for in a grant meeting about cathode and electrode interactions. And we didn't have a good model, so we thought, okay, let's take one of these and see. And I was very surprised that the model fitted on the materials project, small inorganic crystals, didn't explode when it was run on a sort of a half cell of a battery. And so I asked my students to try it on whatever was on their screen. And it was kind of incredible that the batteries didn't explode, and then perovskites were kind of okay, and aqueous interfaces showed the right chemical behavior, and the sulfur rings polymerized when they needed to, and amorphous carbon quenched from liquid kind of worked well, and hydrogen combustion looked sensible. So this was really, really unexpected. And then within a few weeks, friends of the group and friends of friends started emailing us that they wanted to try this model that they've heard about. And so we ended up with sort of 40 different applications all over materials chemistry. And seeing that this model that we fitted to small inorganic crystals behaved really rather sensibly and produced nanosecond long trajectories that kind of made chemical sense. And this was very, very bizarre. So you can read the outcome of this frenzied few weeks of work in a paper that's now almost a year old. We are working, it's under review, and we're working on a revision of the original model. But this is a collaboration of about 20 groups, because each of them is an expert on some application. And what we found overall is really, as I said, the model works for anything you throw at it and gives you kind of sensible outputs, like with the quality of what you would expect from a semi-empirical model, in that it's chemically sensible. You can run a long trajectory. But then you can also refine. So and in fact, that's the revision. That's not in the original archive, and that's manuscript, and that's what we are now working on. But even the original model is quite sensible for something like MOFs, which are nowhere near the database. Original database doesn't contain any MOFs, and here you take MOF 74, and you put CO2 in it. You compute the free energy map of that CO2 in that pore, and this is what the map you get, and this is what you get with an ML potential, which has been custom fitted to this particular MOF using giant quantum calculations as data. But because our model works off the shelf, you can just swap all the metal atoms, swap out the organic linker, and you can study the free energy map of arbitrary MOFs using this model. Here's hydrogen combustion. So you start out with just hydrogen and oxygen, you let it go, and you get really quite sensible burning. You burn this to get mostly water, but then you look at the intermediates, and all of them make chemical sense, even though nothing like this was in the training set. And if you look at in a bit more detail about you look at the thermochemistry of all these reactions that are taking place, you get, if you squint at this bar chart, which shows the experimental thermochemistry, experimental energy difference between the reactants and products, the couple of different MACE models. We have two different sizes, in fact, 3, small, medium, and large. And I've thrown reactive into this plot. It shows you that qualitatively, you basically get what the reactive model, which is painstakingly fitted to reproduce this kind of combustion, but you get it off the shelf. So this is sort of what you can get from this model for things that it wasn't fitted to. And here's another example. I won't go through every single detail. These are pictures from that manuscript. This is for heterogeneous catalysis. And here's again an example of success and failure in some way. So what you see here, these are steps of a reaction on copper. And what you see is MACE MP. So the materials project with MACE is the orange. And if you then point evaluate, single point, you get the black curve. So, there is an error. These different fragments bind with a different binding energy, but generally the troughs and valleys are correct. So you can explore the reaction network, and with just a few, you throw in a few DFT calculations of this system, and these curves then align correctly. So qualitatively correct, and then quantitatively when you refine. That's the methodology that this suggests. Here's another example of a full battery simulation of 2,000 atoms with anode, cathode, and electrolyte, and you get qualitatively the right kind of chemistry happening. In fact, you get oxygen loss from the cathode here, the nickel, manganese, cobalt cathode, as you should. And then you can go in and study the details and perhaps refine. The computational efficiency is where it's all at, right? That's the whole point. So this is the number of atoms, and this is log 10 of million steps per day. So a nanosecond per day is here. So that's here, that's log 0, right? Log 10 of 1 is 0. So this is 1 million steps per day, and we can do about 10 nanoseconds per day on a single GPU using CUDA kernels that are now publicly available. And we have a CPU implementation due to Chuck Witt, and that can MPI parallelize this, so we can do 1 million atoms, and then you can do 100 picoseconds per day. And that's on 700 cores, but you can go down to about 50 atoms per core. So if you have a lot of CPU cores, you can scale to sort of arbitrary system sizes with sort of basically linear scaling. And so really what we have is foundation models, I would say, that can tackle anything in the periodic table. They don't quite come here. They come over here in accuracy. The foundation model gives you very large length scales and time scales at a sort of semi-empirical quality, and then you can fine-tune with just a tiny handful of new configurations and, a few hours of further training, which then gives you ab initio accuracy on the specific system that you fine tune for. And here's a more fun slide to kind of close off, which is a system of, the periodic table, which you can run. Every atom here is represented by its own element. So we have force fields that can use thousands of atoms, tens of nanoseconds, ab initio accuracy when fine-tuned. And the compute is not huge. So even to train the original foundation model, it's a couple of thousand GPU hours. It's an academic group can afford it. You don't need the Facebooks and the Microsofts to play this game. So this is all open. This is all academically free. The models and the source code of MACE. We also have a commercial partner. So MACE is now in Material Studio. That's sold by Dassault Systems. So you can select the MACE MP0 force field in their MD driver and run using all these different systems. So thanks very much. I'll sort of stop the share and happy to answer questions if you have any. Thank you very much.
Thank you, Gábor. That was a very interesting talk. Yes, so we have a few questions. And probably I'll just ask Stephanie to speak up if you can. If you cannot, I can read out the question, but how about you speak up, Stephanie?
Okay, thank you so much. Yeah, so I had two questions for you. So the first question was just, you threw out there that 1 MeV accuracy was sufficient for most material properties. And I was curious, like, are there some references you'd recommend, like, following up on that explore that particular topic in a bit more depth, because I'm really interested in that. And then the second question is, you mentioned refining the model to get quantitative accuracy. So that sounds to me like a transfer learning process, but I was wondering if you could elaborate on your steps there in a little bit more depth.
Yeah.
Thank you so much.
So thank you. So the millieV, so that question of the general question of how does accuracy of a potential energy surface, according to some measure, right, Boltzmann or your data or something else, how does that translate to a property accuracy is a super interesting question. And a question, I think, of which we barely scratched the surface, and much will be thought about and written about this in the future, because now we, community, the world has models with which you can study this, because we have models that can be refined and tested against property prediction. So what I've given you there is sort of is a rule of thumb that I picked up over the years. You can go back to that paper on tungsten. We have a paper a bit later, 2018, on silicon, the first kind of general model that's generally applicable across many phases and many properties. And there we test different accuracies, models that have different accuracy point-wise on energies and forces, and then see what accuracy they produce in downstream properties. In general, that mapping, that function, I expect it to be quite complicated, depend on the property, depend on the material. And in very few cases, you can study it kind of with analytic tools. I think, accuracy in phonons is something which you can connect back to accuracy to forces. But it's not trivial, because, you need to get good phonons, you need to essentially get the Hessian correct. You need to get force constants right. But what's the accuracy? Is it an absolute accuracy on the forces or a relative accuracy? Do you need small forces to be better in absolute terms than large forces? So those are all kind of questions that are there to be asked and answered. And you can do that maybe analytically for a single phase, but then not across multiple phases. So I don't have a more satisfying answer for you. It's really just that I think this is a question that we can now start answering. And empirically, we see that as we go through, 100 millieV per atom, 10 millieV per atom, 1 millieV per atom. They're around 1 millieV per atom. Lots and lots of properties now start to look very, very good. That's sort of my and that's for materials. For molecules, intermolecular interactions are smaller, are much more delicate, and many very important properties will depend on those, like densities of liquids, where a simple millieV per atom energy accuracy will not be predictive. You need other properties that are more directly targeted at intermolecular interactions that are relevant. So your second question is on the fine-tuning. So there are many different ways to do that. You can take the existing model and continue training it on a new data set that you provide, perhaps add to the data set. Now, the problem with just training on a new data set is that initially you'll get just better errors on your new data, but eventually you get excellent errors on new data, but you kind of forget the good properties of the old data. And in particular, this good stability of long MDs is gone if you train for many epochs on a handful of new data. So what we end up doing recently, and this hasn't been published yet, but it's certainly there in the code, is it's something called multi-head fine-tuning with replay. So we take, it's a complicated ML kind of phrase, but what essentially means is that you take a little bit of the old data, a little bit of the new data, and you try to fit to both. And when you do that, you get a model that is very good on your new data, but it still has the old good properties of the old model that it's able to carry out long MDs. And that lots and lots of people have found success with that. And you can already find papers on the archive that do that kind of thing, that do that kind of refinement.
Thank you so much for such a complete answer on that. I appreciate it.
Nikhil, you're muted. I can't hear you.
Oh, sorry about that. Yeah, good. Thank you. So I have a couple of questions. You were showing a slide which was comparing ACE and MACE, and you were showing how inter and intramolecular forces are captured better, in addition to, of course, the forces. So I always had this question: is the notion of interatomic force even how do you even define that, in the sense that you could construct potentials which have identical forces, two different potential identical forces, but very different interatomic forces, right? It goes back to the question of what exactly is interatomic or intermolecular forces.
The definition is kind of simple, right? I mean, you can take, it's an operation where it's not a property of a single configuration, right? So I take the condensed phase configuration and I choose to excise each molecule, put it in vacuum, compute the forces, do that for all molecules, sum them up, and those are the intramolecular forces. And now I subtract that from the condensed phase calculation, and that's the intermolecular force. So it's not, you're right, it's not a property of a single configuration, but it is a property of your energy model. So if you have a model like DFT or a force field, you can do that. And the question is, what training data do you need to get it right? First of all, it's a very interesting number. This property, this combined property, is very interesting. It controls important properties like density and diffusivity of a molecular solid or liquid. And it throws these questions. So what data do you need to get it right? And different architectures which might appear similar for, like, say, total energies and forces, do they show different behavior, different accuracy when trained on the same data? And the answer is massively so. And, if you ask me, can I pinpoint exactly why that is, which aspect of the model architecture leads to this, the answer is not really. We don't fully yet understand it.
So you said that MACE has some nonlinearities, and somehow that...
Well, it's the second round. right? So MACE, these are the two differences, is how MACE is different from ACE, is that its degrees of freedom. So ACE is a polynomial model. The degrees of freedom are coefficients of polynomials. MACE has, because we use this deep learning technology of linearly recombining our descriptors at each stage, those degrees of freedom multiply together. So you have polynomials. If you did MACE only one round of atomic cluster expansion, you would still have these degrees of freedom that multiply together. So you could think of that as a kind of tensor decomposition. But that's one aspect of it. It's like a tensor train. And then the other aspect is that you do this twice. So then you are now multiplying polynomials on different sites together. So you could think of that as a kind of sparsification, or again, a kind of tensor, making kind of graph tensor network, essentially. But there's no activation function here. There's no nonlinear activation like you normally use in a neural network. It's all polynomials and their products, but in a very kind of chemically sensible way. That's the difference. But how does that translate, and why does that translate into this dramatically better representation of partitioning of inter and intra? I can't answer that. That's the frontier of our knowledge.
You mentioned in passing that the ACE and MACE are complete bases, but is a SOAP also complete?
No, SOAP is not. And that's I have a whole bunch of slides on that. In a longer talk, I would talk about that. Very, very interesting mathematical discovery of the late 2010s is that three-body representation, so angles and distances around an atom, do not give you a complete representation. We have counterexamples of environments which have the same angles. And so this that SOAP and Bela-Parnello G2, G3 and DeepMD are essentially incomplete in this dramatic way that you can show configurations where they would give the same representation, even though the configurations are different. And they're not crazy configurations. They're perfectly sensible atomic configurations. And I think this is the big dividing line between old technology, between 2007 and 2019, and new technology of ACE, which when you go to high body order, actually it's not known whether ACE is complete, whether any finite ACE representation is complete, but MACE is known to be complete. So that's a very recent result. That's last year by a bunch of mathematicians from Chile who have demonstrated constructively that given the ACE features after the second layer. So this is another possibility, right? That you need to do this ACE iteration twice. And after the second layer, you can now reconstruct uniquely the local environment.
I see. Interesting. And this whole notion of able to predict properties of large systems from data, training data on small clusters. I mean, there's a whole bunch of works coming out now. I always wondered, is the training done on sort of relaxed configurations of little clusters, or are they unrelaxed?
No clusters. None of them are clusters. They're periodic. In MACE MP, they're all periodic.
I see.
Crystals. But they are close to relaxed, not entirely, because the way Materials Project has generated itself is that you take experimental structures and then you relax them with DFT. So they are kind of close to equilibrium, but not quite. And I would say that's it's super interesting that's enough to get you chemistry, including reactions, including barriers, but it is not the ideal training set. So and people have shown since then that generally the barriers that this foundation model predicts are a bit small. So things melt a bit too low. Bulk moduli are a bit small. And you don't need much. You just need a bit more non-equilibrium. You need to displace the atoms a bit randomly, and then you fix that. So I would say that is kind of remarkable that near equilibrium is gives you such a wide range of transferability. But then now there's lots and lots of work going on in generalizing these data sets and optimizing them. And of course, the first thing I would do is to rattle the atoms a bit more.
Nice. I mean, my follow-up question was, is it possible that this is doing fantastic for equilibrated structures, whereas if you kind of study kinetic properties like
No. Kinetic properties. No, it's
like
quite
that.
good. It's quite good with and but not perfect, of course. But it's not like it goes crazy like the old models did, right? You take a Baylor Parnello, you take a stopgap, our old models, and you go to something completely different, and it's like goes crazy. The potential is bananas. Whereas the Mace MP model is quite reasonable. Very far from it. I mean, you saw that in the combustion example.
Yes. Very interesting. All right. So if there are any other questions from others, you can speak up. Otherwise, we are almost time to close the webinar. Again, thank you so much, Professor Csányi. That was a very interesting talk. With this, we are closing this month's webinar. See you all next time.
Great. Thanks. Bye.